Hello everyone, thank you for attending my presentation. I'm Seongyo Jeong, a graduate student at Handong Global University. This is the presentation outline. In my research, I focus on free space detection using automotive radar. Free space detection is crucial for the automotive driving. The common method for free space detection is generating occupancy grid map, which we call OGM. For OGM generation, we divide the environment into grid cells and assign a probability of occupancy to each cell. Camera and LiDAR are commonly used for OGM generation because of their high resolution data. However, these sensors have limitations such as short detection range and environmental sensitivity. In contrast, radar sensor has a long detection range, and it can even detect non-line of sight targets due to RF diffraction. This makes radar useful for high-speed driving and in complex environments. However, using commercial radar for free space detection has its own challenge. The main technical issue is sparsity of radar detections because of the low angular resolution of commercial radar. Existing methods like inverse sensor model and deep learning models are invalid for commercial radar because they assume using high resolution radar. The goal of my research is to develop a new free space detection method that can work effectively with sparse commercial radar data. The proposed method has three key components. The first one is virtual detection augmentation. I generate additional virtual detections using radar attributes like Doppler and bounding box. It will address the sparsity issue of radar detections. Next one is multi-frame data overlap. I overlap radar detections from multiple time frames to increase the overall detection density. It also helpful to cope with the sparsity issue. The final one is OGM generation model. I use an auto-encoder neural network to infer free space from the radar detection image. The first idea is virtual detection generation. I utilize radar data attributes like bounding box and Doppler to create a dense detection image. The detailed methodologies is in this table. I classified the driving environment into 4 parts and assigned probabilities for the grids that detection is obtained. The first is stationary object. These are detections with very low Doppler, and I assign the probability as 0. Probability 0 will be black color, and probability 1 will be white color in the detection image. The next part is moving object. I use Doppler and dynamic model to predict future vehicle movement and assign 0.7. This is direct information about road boundary because the vehicle tends to follow the road boundary. The third part is occupied area. I use bounding box information to identify areas occupied by object and assign 0.9. Finally, if there is no detection in certain grid, it is free space environment and the probability is 1. To cope with the radar sparsity, I also implement a multi-frame data overlap technique. This includes mapping radar detections from previous frames to the current frame. To do this, I use vehicle dynamics such as position and heading angle history. By overlapping detections from multiple frames, we can also improve the the overall detection density. Unfortunately, we cannot get the OGM from the detection image direct because mm, the nonlinear relationship between radar detections and road boundary. To solve this relationship, I designed an autoencoder network with skip connections. The autoencoder infers spatial correlations between the input detection image and output OGM. And skip connection combined low-level features with high-level semantic information. This network can find the nonlinear relationships between input and output by training. Finally, I can predict OGM from the trained network. The note to show the superior performance of the proposed method, I have carried out some simulations. The radar specifications are as follows. The radar's detection range is 250 meters, and the azimuth resolution is 3.2 degrees. To benchmark our method, we compared it against three baseline methods. First method is camera-based method called surround OCC, and second is LiDAR-based method, it called spheroformers. And the radar-based method baseline is use only raw detections. To evaluate proposed method, we select 3 test scenarios from the Lucene dataset. The first scenario is to evaluate the capability to handle occlusions. And second is for the performance in low light conditions. And third is demonstrates to the robustness of our method in rainy conditions. This is first scenario. In this scenario, we can check the effect of occlusion. There are many surrounding cars, and they make difficult to generate camera and LiDAR OGM. But the proposed method produce superior free space detection result, even in the presence of occlusion. It seems more clearly for long-range detection. In the next scenario, we can check the effect of low light. This is a nighttime driving situation, and since LiDAR and camera are optical sensors, their performance is influenced by the low light condition. But our method, radar-based method, offers consistent performance regardless of lighting condition. In the final scenario, we can check the effect of humidity. In rainy conditions, LiDAR and camera are affected by humidity or the raindrops. But our method maintains robust performance in rainy conditions and detection range. This is conclusion of this presentation. I have proposed a free space detection method using low resolution commercial automotive radar. To cope with the problem due to detection sparsity, there are 3 key ideas was used. The first is detection augmentation, and second is multi-frame overlap, and third is OGM generation model. Through simulation, we noticed that our method have several advantages over the existing free space detection method. Our method is robust to environmental change, and our method have extended free space detection range. Over all scenarios, our method achieved over 15% average F1 score improvement compared to previous method. Thank you for attention.